Good morning. Today we'll discuss a topic called finite difference formulation. In the previous discussion, what we have seen is what is finite differences. What are finite differences that we have seen? Now, in this particular lecture, what we will see is how to transform the partial differential equation into a finite difference equation. So that is called the finite difference formulation. Now, myself, I am P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. This topic is for 4th year Mechanical Engineering students and the subject name is Computational Fluid Dynamics. Now, here in finite difference formulation, we have two schemes or two methods or two approaches. One is explicit approach, the other one is implicit approach. So why it is called explicit approach and why it is called implicit approach, that we have to see. And what are these different methods that are coming under explicit approach and implicit approach. Now the explicit approach, here each differential equation contains only one unknown. If the finite difference equation is having only one unknown, then it is called explicit scheme or explicit approach. If the finite difference equation that we have derived is having more than one unknowns, then it is called implicit approach. Okay, so that is the starting point of this discussion. So what is explicit approach and what is implicit approach? So explicit approach means the finite difference equation is having only one unknown, and the implicit approach means the finite difference equation is having more than one unknowns. Now here the dependent variable at time delta t, okay, time t plus delta t can be obtained explicitly from the known results at time t. So here we have only one unknown. In explicit approach, we have only one unknown, and that is at a time t plus delta t. So this unknown can be derived from the known values, like say suppose this is n plus 1 or t plus delta t time. Okay, this is t and this is t plus delta t, or sometimes we can call it as this is nth time interval and this is n plus 1th time interval. Now here this is only one unknown in our finite difference equation, and here these are the three known terms, because we are solving the equation at n plus 1th time interval. So we have already the values of nth time interval. So if we already have nth time interval values, and using all those values, if I am finding the n plus 1th time interval, only one term, then it is called an explicit scheme. And the figure here is showing the grid location. So the grid points location at n plus 1th time, and this is at nth time. Now thus the value of dependent variables at time level is known from a previous solution or given initial data. So here the nth level can be the initial data or boundary conditions, and the n plus 1th term is the unknown things. So suppose this is nth term, nth level, we have the values, we have given initial data or boundary conditions, and we are finding it n plus 1th term, and using these nth level times, and further what we do, we find out the n plus 2 level terms using the n plus 1 terms. So this kind of approach is called time marching approach. Okay, we are marching in time. So we are finding all the values at nth time interval, and using all those values we are finding the n plus 1th time interval, and using all those values we are finding the values at n plus 2 time interval. So okay, this is called the time marching solutions. So what are these explicit schemes? There are three explicit schemes that we are going to discuss now, and this is the FTCS, forward in time and central in space. Okay, so this is the grid location that is shown in the figure, and what it shows here is these are the known values at nth time, and this is unknown value at n plus 1th time. So this is the equation that we are assuming. This is a parabolic equation, and it is function of time and space. The variable u, velocity u, is function of time and space. So it is a one-dimensional problem. Okay, here only x is there, so it is a one-dimensional problem. Now the time derivative is replaced with forward difference, and the space derivative is replaced with a central difference. In the previous section we have seen what is forward difference, what is backward difference, what is central difference. So here we are using two things. One is forward difference in time, and the other one is central difference in space. So if I use that, the partial differential equation is transformed into this finite difference equation. So in this finite difference equation, this is we are at n plus 1 and we are using nth term, so it is a forward in time, and we are at ith location, we are using I plus 1 and I minus 1 values, so it is called central difference in space. Now if I modify this equation, so if I modify that equation, what happens is I will get ui power n plus 1 is equal to ui power n into d. This is d is equal to the diffusion number delta t by delta x whole square, and ui plus 1 power n minus ui power n plus ui minus 1 power n. So this is the equation that we got. Now if I observe this equation, what are the unknowns here? So this is the only unknown that I have. So what is this? This is the n plus 1th time interval where we are calculating, and this is only unknown. So we already have the values at nth time interval. So all these values are known values. So here only one unknown is there, and it is at time t is equal to t plus delta t, and it can be explicitly derived from the results at time t. Okay, or and time n plus 1th n plus 1th time interval, you are using nth time interval and finding the values directly. So here the equations are very simple, and the accuracy of this scheme is delta x in time. So this is a first order accurate in time and a second order accurate in space. And the stability, coming to stability of this approach, the stability of the solution using this approach, it is a conditionally stable one. Okay, it is a conditionally stable one. What is the condition? The diffusion number must be equal to 0.5. Okay, it is less than or equal to 0.5. The diffusion number must be less than or equal to 0.5. This is the condition for the stability of this finite difference formulation. So what do you mean by that? It is less than or equal to 0.5. So say suppose if I take here delta t must be equal to 0.5 delta x whole square. Okay, so the delta x is the grid space between two nodes. Okay, the distance between two nodes is delta x. Now the increment in time, how should be the increment in time? It should be the square of delta x. So it is very less. So this delta t must be very less. The time difference between two successive iterations, two successive time steps must be very small. So that then only this FTCS is a stable one. So next approach. So the next one is Richardson approach or Richardson scheme, or otherwise it is called as central in time and central in space. So the grid point location is shown in here. Now here what is happening is we are using the central difference in time as well. So the central difference in time means these are the two, ui n plus 1 and ui n minus 1 are used for time, and what we are doing, we are taking the central difference I plus 1, I minus 1 for this space. Okay, we are using the central difference in space and the central difference is in time as well. So again we are taking the same parabolic equation, using the same parabolic equation, that's why I given the same number 1 here. The first equation that we used for FTCS, the same equation I am taking here and applying this CTCS, the central in time and the central in space. Now what is the order of accuracy of this? The order of accuracy is delta x second order in space and second order in time. Okay, but unfortunately this method is unstable whatever condition you may apply. Okay, whatever condition you may impose on this on this method, the solution is unstable. Okay, so this Richardson scheme or CTCS scheme is of no practical value. So they have derived this equation and found that it is unconditionally unstable, so it is not used. So what they did is they have modified this Richardson scheme, and what they did, they have derived another scheme. We will see that in the next slide. Now here this what type of, whether it is an explicit scheme or an implicit scheme. So to see that, what we are doing is we have rearranged the finite difference equation. This is the finite difference equation that we have. So what we are doing, I am taking this delta 2 into delta t this side, and other things I am keeping like that. So if I do like that, ui n plus 1, this is a unknown value. We are at n and n minus 1 is already known. So here a time time step n time step and n minus 1 time step values are already known, and we have to find what is n plus 1th time step. So it is only one unknown is there, and all the known values are used to find the unknown value. But again I am saying, unfortunately it is not a stable one, how small the time step may be. So the delta t may be, we can take any very very small time step, but still it is a unstable using, it is seen that it is unstable using the stability analysis methods. Now the Richardson method, which was unstable, it is modified. Okay, it is modified by Dufort and Frankel, and it is called as a Dufort-Frankel scheme. So what they did is they eliminated this uin, that term they have eliminated. So in place of uin, what they have taken is they have taken the average of ui n plus 1 and ui n plus 1 and ui n minus 1. Okay, so this is same. This is a central difference in time, and in central difference in space, what they have done is they have taken the average of, they have taken uin. This is the term that we had in the central difference equation previously. Now in place of that, what we have they have taken is ui n plus 1 plus ui n minus 1 divided by 2. So this average they have taken for uin, and they found that it is a stable one. Okay, previously just by doing a small modification for this Richardson scheme, they have found that it is a very stable equation, very stable solution. This finite difference formulation is a very stable scheme. Okay, now if I rearrange this, what will happen? I will get here ui n plus 1 is there, and here also ui n plus 1 is there, and here this 2 into delta t, if I bring this side, it will become 2 into delta t by delta x whole square, and this is equal to 2. This is equal to 2D, because the diffusion number delta t by delta x square is equal to D. So if diffusion number delta t by delta x square is equal to D, then this is equal to 2D. Now if I substitute that one here, what will happen? I will have ui n plus 1, and here it is a 2 into D into ui n plus 1. So if I bring that one here, minus will become plus. So it is 1 plus 2D into ui n plus 1. And similarly, what I will have ui, here ui I plus 1 n is there. ui n plus 1 ui plus 1 n is as it is, and here ui minus 1 n, this also as it is. And it is multiplied with 2D, because delta t and delta x square is there, and it is multiplied whole. So I will get 2 into D here. Now there is another term. What is this? ui n minus 1. So this ui n minus 1 is there, and here it is ui n minus 1. So it will become here ui n minus 1. Okay. So this again here, this is unknown value, and this is known value, this is known value, this is also known value. So using all these known values, directly we can find out what is the unknown value. So it is an explicit scheme. Now here, this by just the small modification, it has become unconditionally stable. So without any condition, it is shown that in the stability analysis that this method, the Dufort-Frankel method, is a stable one without any conditions. Okay. Now the delta t must be very, very small. Okay, the delta t must be very, very small as compared to the delta, the time step, the time step in space. I mean the difference between two space nodes must be very, the time step between two intervals must be very small as compared to this delta x. So that is the only condition here. Okay. But here what we need is to start the computation, we need values of n and n plus n minus. So n values we need to know, and n minus 1 values also we need to know. But at the first interval we don't have the values of n minus 1. So what we do is we take two sets of initial data, or first step we use any other method. So the first iteration, for finding the nth location. So suppose I have, this is n minus 1 and this is n and n plus 1. So this is say suppose this is 0. I am starting, this is the first iteration I am doing. I have only one value. I don't have this value before that, prior to that. So what we do is we can take two initial data, or we can use the one time step method for the first iteration, and further we can use this Dufort-Frankel scheme. So this Dufort-Frankel scheme is a slight modification for the Richardson scheme, at it is an unconditionally stable scheme or approach. Then the next one is implicit approach. As I already said, the implicit approach, say suppose this is the grid point location that we have. In implicit method, what we do is we use more unknowns in the finite difference equation. We have more unknowns at n plus 1th location, and we have some known values at nth location. So here unknowns are more than 1. When unknowns are more than 1, what we need is we have to formulate the finite difference equation for all the nodes, and we have to get some matrices out of that, and we have to solve. So it is we need simultaneous solution for finite difference equations at all grid points. Okay. So simultaneously, one by one we cannot solve. We have to solve all the grid point locations simultaneously. So the computation is very difficult. Here the computation time will be more. Okay, it becomes a little complex. So the computation of unknowns would require a set of coupled finite differential equations. So we with one finite difference equation we cannot find the solutions. We need, say suppose in this case we have three unknowns, so we need at least three finite difference equations. So using three finite difference equations you can solve this. We can find the solution for this using this method. So because these implicit methods are usually involved in manipulations of large matrices. Here I have three unknowns. Say suppose four unknowns or five unknowns are there. Then whatever the case may be, I have to formulate the finite differences equation and transform them into matrices and then manipulate these matrices to get the solutions. So the important thing is, one finite difference equation will not give me the solution. I need to solve many finite difference equations simultaneously to get the solution. So this is the first method of implicit scheme. So what is this scheme? This is backward in time and central in space. So here we are at n plus 1th time, but we are going back and using n plus nth term. So it is a backward in time and central in space. So if I apply this the backward difference in time and the central difference in space, using that what we'll have is the method called the Laasonen method or the backward in time central in space BTCS scheme. So this is the equation that we were using from the beginning. This is the parabolic equation which is giving as u as a function of space and time. It is a one-dimensional problem. So using this, for this what I am doing, I am applying this backward difference in time and central difference in space. If I apply that, I will get this equation. Now if I rearrange this, what I will get is something like this. Okay. So here d is the diffusion term and that is equal to delta t by delta x square. Okay, d is equal to that. And in this equation, how many unknowns are there? I don't know the value at n plus 1 of u, and I don't know the value of n plus 1 I plus 1, and I don't know the value of n plus 1 I minus 1. So I have three unknowns here and I have only one unknown. So the three unknowns are to be found out, and so the dependent variables at time t plus 1 cannot be directly obtained. We need to manipulate the matrices which are involved in the three unknowns using the three different finite difference equations. Okay, so this kind of approach is called an implicit approach. So in implicit approach, we have to use many finite difference equations for finding the solution at any particular time. So the next approach in next method in implicit scheme is a Crank-Nicolson scheme. So this is another scheme that is there for in implicit approach. So what is this Crank-Nicolson scheme? So what we are doing here is this is the backward in time. Okay, backward in time, and the space derivative. The space derivative, what I am doing here is I am taking the average of central difference in n plus 1th location and central difference in nth location. So we have two locations n and n1 plus 1. At both levels, what I am doing, I am taking the central difference in space and taking the average of the central difference in space for nth location and n plus 1th location. So by doing so, this parabolic equation that we are assuming from the beginning is transformed into the finite difference equation like this. So this is the finite difference equation that we have, and in this finite difference equation, this is the backward difference, and this is the average of two central differences at nth level and n plus 1th level. Now, if I observe it, what we can say is it is an average of FTCS scheme and BTCS scheme. So in FTCS scheme, I am using this central difference for space, and in BTCS scheme, I am using this central difference for space. So I am taking the average of these two, and this is same for both FTCS and BTCS scheme. So this is this Crank-Nicolson scheme can be stated as an average of the FTCS scheme and BTCS scheme. So what is this FTCS scheme? It is a forward difference, central in space, and here it is backward in time and central in space. Forward in time, central in space, backward in time, central in space. If I take average of this, I will get the Crank-Nicolson scheme. Now, if I rearrange these terms here, this equation, if I rearrange, I can get a big equation, and which will have the unknowns n plus 1, 1, 2, 3. Three unknowns are there, and here I have, this is known value, this is known, known. So I have 3 known values and 3 unknown values, and using that 3 known and unknown values, see here, this is unknown value, this is unknown, this is unknown, and this is known value, known value, known value. So I have previously one known value, and I am finding the values of 3 unknown values. Now here I have 3 known values and as well as 3 unknown values. And the second, the time difference, the time one can be approximated as a central difference with the time step delta x by 2, delta t by 2. If I take the time step is delta t by 2, I can say it as a central difference scheme. Actually, it is a forward difference scheme, a backward difference scheme, but we can consider it as a central difference of delta t by 2 time step. With delta t time step, it is a backward difference. But if it is delta t by 2, it is a central difference. So that is the side point. But if I rearrange this equation, I will get this equation, and this is equal to, this is having 1 unknown, 2 unknowns and 3 unknowns. 3 unknowns are there, and I have 1, 2, 3, 3 known values are there. And it is a second order accurate in time and second order accurate in space. Okay, this is a second order accurate in time and second order accurate in space, considering that it is a central difference of time step delta t by 2. Okay. Now, so what is the advantage of this? It is an unconditionally stable one. So previously also we have the Dufort scheme, that is also an unconditionally stable one, and the Crank-Nicolson scheme is an unconditionally stable one. So what we have seen till now, we have seen that explicit schemes are there, implicit schemes are there, and in explicit scheme we find only one unknown at a time using more known terms, and in implicit scheme we use one or more known values and find more than one unknowns in each finite difference equation. So in explicit scheme we use, it is very simple, one node at a time we can calculate. But in implicit scheme, for all the nodes we have to find the formulate the finite difference equation, and we have to solve all the equations simultaneously. So that is the difference. Now there is a general formulation called beta formulation. Now what is this beta formulation? So already we have done so many formulations like FTCS scheme, Crank-Nicolson scheme, etc. Now all these schemes can be represented in this beta formulation. So this is the for equation that we are taking model equation, and for this equation I am applying the backward difference, and I am putting an alpha here. What is alpha? Alpha is equal to, if I have an alpha here, I will get alpha here, and here this is the central difference at a time interval of n plus 1, and this is central difference at a time interval of n. Now, if this is beta and this is 1 minus beta, if the beta is equal to 0, if beta is equal to 0, what will happen? I will get only this element, and it is forward in time and central in space approach. If beta is equal to half, what happens? It will become, here also I will get half and here also I will get half. What is that? Average of the FTCS and BTCS, and that is nothing but the Crank-Nicolson scheme. Now, if beta is more than 1, more than half, if beta is more than half, it will become unconditionally unstable. Whatever condition it may put, it will be if it is beta is less between half and 1, it is unconditionally stable, and if it is beta is 0 to half, it will be conditionally stable. Okay, there we have seen that FTCS when D is less than or equal to 0.5, it is stable. So there is a condition, but it is stable. FTCS scheme is stable with a condition, and Crank-Nicolson scheme is stable without any condition. So that is what is about this beta formulation. So beta formulation can be considered as a generalized formulation for all these schemes. So based on the value of beta, it can be an FTCS scheme or it can be a Crank-Nicolson scheme. So finally, we will summarize with the differences between the explicit approach and implicit approach. So the explicit approach, we are finding one node at a time. So it is very simple in setting up the formulation, finite difference formulation, and writing the program as well. But in implicit approach, what is there is we have to do formulation for all the nodes at a time, and we have to use matrices for solving this equation. So it is a little more complicated than explicit approach. So for given delta x and delta t must be less than the limit imposed by the stability criteria. Okay, so we have seen D is less than or equal to 0.5. That is a condition for stability. So the delta x, based on the delta x value, we have to define the delta t value. Okay, and the delta t will be much less as compared to delta x. But in case of implicit scheme, the delta t value can be slightly higher because there is no condition here. So the delta t values can be little higher. So what we can do is we can calculate at small intervals of time. Say suppose in explicit approach, I need 10 time steps, but in implicit approach I can do the same thing with 4 time steps. So that is the one advantage. Now using considerably more time steps. So here I need more time steps. So this results in more computation time. Okay, here I need more time steps, so the computation time will be high. Here I need less time steps, so the computation time is also less, because less times I have to calculate values, so the time taken is less. Here I have to calculate more number of time steps, so I need more computational time. Now here simple equations are usually required to be manipulated. So here one unknown is there, one equation is there, generally it will be the case, and it is easy for each time step. The calculation is very small. But here matrices are to be manipulated because more unknowns are to be calculated at each time step. So all the nodes at n plus 1 are to be formulated, and then use the matrices and calculate the values all at the same time. So it requires for each time step, okay, even though the number of time steps are less, here 10 time steps are required, sometimes even 16 time steps are required, here only 4 time steps are required. But for each time step, the time for solution, the computational time is more in case of implicit scheme, but here for each time step, the computational time is very less. Now, I said the delta t must be very small in explicit approach. So the delta t is very small. So the error, the truncation error is also small. So this kind of approach will give an accurate solution. The explicit approaches will give accurate solutions. If I take the truncation error small and time step is also very small, I will get very accurate values. But the very small time steps will lead to more computational time. But here large time steps can be taken, so the errors also will be very large, so it may not give an accurate solution. So we have to reduce, we have to take an reasonable value of time step so that we can get an accurate value in case of an implicit scheme. Okay, this in explicit scheme definitely we have to take a small value, so definitely we will get an accurate solution. But in implicit scheme we have a freedom to take a larger time steps, but we have to exercise some limitations and we have to take a proper time step so that we can get an accurate solution. So this is about the explicit schemes and implicit schemes. So what we have seen, what are different finite difference formulation schemes, okay, and we have two schemes. One is explicit scheme and the other classification is implicit scheme, implicit type. Explicit type, what we are doing, we are using one unknown, and so the finite difference equation we have to solve at each node, okay. But in implicit scheme we have more unknowns because we are we are using more nodes at a given, but in a given finite difference equation. So we have to write the finite difference equation for all the nodes and finally you can solve. So the explicit is having some advantages and implicit is having some advantages. So we have to use our intelligence and find which is better for our situation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.